Remember last time we said materials are never fully elastic, means reversible, instantaneous reaction to load, or fully plastic, means the whole deformation turns into permanent deformation. Normally, at lower strains, we have elastic, linear elastic behavior, and it turns to plastic behavior later when the strain is larger. And this is a simplified model, so this complicated curve is approximated by a bilinear relationship. You see that if you read the problem statement, you see that yield point, you can also look at it here, is 600 megapascal. It corresponds to the strain of 0.003. So if I were you, I would mark this here. And then at 800, the strain is 0.007. So what we are asked to calculate are these three questions. But you have to be very comfortable with problems like that. So one is, if we apply 650 megapascal, how much strain we will going to have? So to obtain that, we have to find out if you apply 650 megapascal strain, how much strain you are going to have. To do that, let's work here on this figure. To do that, one of the first things we want to do, we want to characterize this stress-strain curve. We can very easily find the elastic modulus, the linear elastic, during the linear elastic portion of this. Let's call this one E1, which is the slope of a stress-strain curve. So let's first calculate E1, and this is more like a chord modulus. So you remember that I told you if the relationship is not fully linear, we are not going to have only one elastic modulus. You are going to have elastic modulus depending on where you are on the curve. This is a simplified version. We only need two elastic moduli to characterize this curve. So let's calculate this if you haven't done it at home. How many actually worked on this problem at home? Okay. I have to send a reminder. I understand it is Monday, there was a weekend. But it can happen that if I ask you to do something at home, then you may see a pop quiz on that the next day. It's kind of dangerous to ignore. So E1 and E2, how to calculate that? So if you read the problem statement, this is 0.003. Let me use a different color here. So E1 will be just the slope of the first line. Here it's kind of, we need to be careful when you write just sigma over epsilon because it depends where we are in the curve. So I add at the bottom, because this is not a linear elastic material anymore, I have to say sigma over epsilon in which strain range. So here I cannot simply say sigma over epsilon because it's not really starting from 0. So it's much more it's really, since it's not starting from 0, we cannot just say sigma over epsilon. If you take sigma over epsilon, it will give you the slope of this line. For example, if you take this point, it will give you the slope of this line instead, which is obviously not what we are looking for. So this is like the derivative, like what we discussed last time, like a chord, more like a chord modulus. And to obtain that, you can see easily graphically that what we can do, for example, is to see how much we are going in the vertical direction over horizontal direction. So this is wrong. For example, if we take the 2 points at the two ends, it's just the slope of the line. And this is why I wrote it here. And that's why I tell you sometimes, just remember to have statements with formulas. Because it's dangerous. If you just say sigma over epsilon, you may get something which is not E2. And this turns out to be okay. Now, if we apply 650, how much strain we are going to have? So now let's try to answer the first part. We are applying 650. If you go to the curve, you land somewhere here. So this is 650. You go to the curve and you see that we are here. So you see that the strain is this much. This much of it, like 0.003, is elastic, and then you have additional strain. So we have to kind of break it up into two parts. So for answering part 1, did we call it 1 or A? Yeah, 1. Becomes almost like geometry. Say, okay, a strain corresponding to a stress equal to 650 megapascal is a summation of the strain in the first part and then strain in the second part. And how do I calculate the strain in the second part? Now it's easy. I know E2. So try to calculate it on your own. See if it all makes sense. You want to calculate that? Yes. You want to calculate the strain at 650. That's the question. If you are ahead of the class and you are done with the first part, look at the other parts and try to work on them on your own. Let me check my answer, and I want to see a few. I saw one correct answer up there. To get this part, we say, okay, how much increase in stress is 650 minus 600, and the E2, here the E2 is the slope. So we need to divide this by E2, which I had somewhere, and everything is in megapascal, so I'm good to go. And if you sum them up, if I have everything right, you get to that. And sometimes people use, there is no unit, but they use inch per inch or millimeter per millimeter. This is something you see. So great. So this is here 0.0198. Makes sense. And then we have the second part. What happens if we release this 650? So try first to draw the unloading curve based on the things we talked about last time. There are two different slopes. So you have this part plus this one. So this is the change in the stress is 650 minus 600, and you just divide it by a slope to get it. It's much easier than trying to make things complicated. Okay, if we unload, with which slope does it go back? Is it E1 or E2? Exactly. So, since we know that, it's going to be easy. So, this is part 1, we finished. Part 2, we are going to unload. And the unloading curve will go parallel to the elastic beginning. And this can be explained microscopically very easily. So now we want to know, what was the question? We want to know what is the permanent strain. How much is the permanent strain? This part will be recovered, and this will be the permanent strain. So I want to draw the permanent strain with a different color. So this is in part 2 permanent strain. But it's not very hard. So we say, okay, the total strain that we had, if the permanent strain will be the total strain which we calculated in part 1 minus how much strain is recovered during unloading. So here we know that this was 0.0198, and the recovery, the calculation is even easier. So it would be just 650 divided by this time E1, which we calculated before, because it goes down like E1, like the slope in the beginning. And if you do the calculations, and if I have done this right, you will get something like this, 0.0165. And this is this point. What happens then? Well, now if you load back again, we are here, and if you go to 625, the question is how much additional strain you are going to have, and what type of a strain is it? This is simple, right? First of all, let's actually decide what type of a strain it is. What happens if I load it to 625? Is it elastic? Yes. Exactly. So if someone tells you, okay, we said that the yield stress is 600, how can you say you have only elastic strain if you load up to 625? How would you answer that question? Exactly, because the loading history matters. Before, when you go to 650, you are doing a strain hardening. You are raising the yield stress. You are making the elastic region longer. So now it goes back to running. I said I needed than 7 miles. Maybe you have noticed there's only 1 or 2 runners here, right? If you go like 3 miles training, you have done this for courses, etc. The next time when you go running, up to 3 miles you are fine. You kind of feel it when you go after 3 miles. Isn't that the case? Yeah. So, and then if you go 5 miles, the next time you feel it not at 3 miles, but at 5 miles. So this same thing happens here. If you apply stress on the material, it hardens to a larger yield stress. So next time, the yield stress is not at 600, but it's at 650. It turns out that this is actually one way to increase the elastic range of metals. You can do that. You pre-stress it to have a larger elastic range. Very simple. So now let's finish this up. So it's very easy to calculate the additional strain. I'm using colors because the figure is becoming complicated. It will be just 625 in this case. Divided by E1. And this is just a tiny amount. And we all agreed that it's elastic because we have increased the yield stress. So now the new yield is 650, but the original yield was 600. That is when the elastic behavior turns into plastic behavior. Good question. It's normally not so clear, cut and clear here. This is a simplified model. Any other questions? Okay, this was a very important problem. So, about 50% of you are taking C P37. Are you doing a stress strain testing for metals in that class? Yes? Oh, the first time is starting today. Well, okay, so we are all in the same situation, which is okay. You may wonder where we get this stress strain test, particularly for metals. The way it is being done is that you have a loading machine, and then you have some standard samples which look like that, like a dome-shaped sample. This is to ensure that the stress distribution is uniform in the middle. And then you measure the strain first deformation using the extensometer. And then you also measure stress. I have some videos because I believe even in 337 we don't do this for metals. So just let's see if it works, hopefully. Yeah, I don't think the sound matters in this case. So basically then you pull on the coupon, the sample, and if the material is dot size, that means if it deforms before failure, as you can see here, it becomes narrower and narrower, as you can see. This is called necking for obvious reasons. And at some point, it snaps. That's in German, that's why it looks so strange. Hello. Okay, and this is a nice video actually, because first you see the apparatus, and you see how it's small and small. And plastics deform differently. And here you see the extensometer. It's nothing else but something that measures the distance in deformation of an object. And you notice that here you also have narrowing, but then you are starting to have near failure. You start to see some parts coming out. Hopefully this happens again this time, please. So basically you are measuring the stress, you are measuring the strain, and that's how you get this curve. But different materials behave differently. Metals, you see necking, and then in polymers, you start seeing some separations toward the end. Yeah, you see? And then you have the... Okay. I'm glad this worked. So something like that. As you can see, the cross-section is changing quite a bit as we are applying the force. So now this comparison between metals and polymers, you kind of saw how different was the failure mechanism. Here we had a lot of necking, and here at some point you started to see these chains coming out, and then you had failure. For metals, if you plot engineering stress, that I want you to remind you that this is when we divide the load by the original cross-sectional area and not the actual cross-sectional area that we saw was 20%. Versus engineering strain, which is also change of length by the original length. The shape looks something like that. In this graph, one thing which is very important is what is marked with TS. And this is the tensile strength. I'm now using the word strength. This is, if you plot engineering stress versus engineering strength, it is the maximum stress that you can achieve. And that's why it's called tensile strength. And you can see that after that you see a large amount of necking, and then rupture happens later. in metals, you are going to see a lot of deformation before they fail. So if you look at the two ones that we tested, if you examine the ruptured surface, you see something like that. It's not very clean. It has an angle and it has deformed a lot. Metals are under what we call ductile materials. They elongate a lot before they actually rupture, as you saw in the videos. Let's just discuss very quickly. We have 1 more minute according to this. It's interesting to note that if you plot the true stress, meaning that if you are dividing the force by the true cross-sectional area as it is changing, the shape of the curve will be different. In engineering, a lot of times we use this, but it's important to be aware that if you would plot the true stress, it would be a lot larger. So I guess we need to stop here also. This is very interesting. And continue next time.